When an object in contact with a surface rotates about an axis that itself is moving, we name that type of motion rolling, which is exactly what we expect by rolling. It's just a formal definition. Here we have an LED on the axis and a red LED on the edge of a wheel as the wheel rolls along a table. And you can see that while the center of the wheel, the axis about which it's rotating, simply translates, any other point does this weird little loop-de-loop, which is called a cycloid. The motion of the cycloid is really remarkably complicated. There's some, I guess, relatively decent math that goes with it, but it's certainly not fun. Luckily, we can treat the rotation and the translation independently most of the time. We'll be concerning ourselves only with the cases of so-called rolling without slipping. That's when there's no skidding involved. So, there's no skidding. We'll sit on what that ends up meaning later. So we again can watch the path of a point, and it does something like this, and goes up and comes back down, and does this. And we can see that there's exactly one revolution of the wheel until it's back in contact. It goes around once. And the center of the wheel has moved forward a distance equal to one circumference in that time. So we see that. But then by definition, the time to make one revolution is the period, right? This is time to make one revolution is the period. And so v, which is delta x over 2 pi r, over delta x over delta t, is 2 pi r over period t, which we can pull out to say is 2 pi over t times r, or is omega r. All right? So the forward velocity has to be omega r. If we were moving along with that same speed, we wouldn't see the wheel roll. We'd see it spinning in place, and each point on the rim would have its own speed, omega r, because remember, that's the tangential speed of a point doing a circle is omega r. The contact point in that case would look like it was moving backward. If we're watching the thing, we're moving along with it, so we're watching it, then it's rotating sort of like this, and so this point seems to be moving that way. But then the whole wheel is dragging that point forward. So when we add the two things, the point in contact does not move. And that's going to be the crucial bit. That's actually what we mean by no skidding, right? A skid is when the thing drags along the floor, where the wheel actually kind of skids and drags on the floor. If there's no skidding, then there can't be any of that dragging, and so the velocity of the point of contact has to be 0. At the moment, it's the point of contact. A little bit later, that piece of the wheel won't be in contact anymore, and will have some other velocity. So if the contact wheel has speed of 0, then it isn't moving, and that's why we call it rolling without slipping. Of course, an instant later, the point that was in contact no longer is, and it continues to move. And a new point has come into contact, and at that moment that it's come into contact, it becomes at rest. Whatever point happens to be touching the ground will also happen to be at momentary rest. All right, so here we have a wheel that rolls without slipping. What is the correct velocity vector for point P on the wheel? Notice that point P is this one. And we know at that moment, well, it is being carried forward by the wheel, but it also has an upward because it's spinning around the wheel. And so the net is that, which is really, that. So it seems like it's C. Drawn a little bit cleaner here, but again, we see the answer is C. Well, we know that V equals omega r, so we can solve that over, and we find out that you get 90 radians per second according to this. Notice the half because we need the radius, not the diameter. A solid cylinder is rolling without slipping across a level surface at 2.7 meters per second. The cylinder has a mass of 3.3 kilograms and a radius of 25 centimeters. What fraction of its total kinetic energy is rotational? And you might want to recall the rotational inertia of a solid disk, or cylinder in this case, is that the rotational inertia is 1/2 mr squared. Here we will say the translational kinetic energy is just 1/2 times the center of mass speed times the velocity squared, 1/2 mv squared. And the rotational energy is 1/2 I omega squared, which we can then process by using the fact that I is 1/2 mr squared, and that omega is v over r. And so when we put all of that together, we find that the rotational energy, kinetic energy, is 1/2 mv squared. All right, we haven't changed the rules. I'm not saying it's not a half mv squared anymore. This is a process that the rotational one is equivalent to 1/2 mv squared. Then we can just kind of do some algebra. We can say, oh, well, then the kinetic energy total is the translational plus the rotational. So it's a 1/2 mv squared plus 1/4 mv squared, which means the total energy is 3/4 mv squared. And the fraction that is in the rotation is just the ratio of 1/4 mv squared to 3/4 mv squared, which is 1/3. Notice that the radius happened to drop out. This will happen a lot when the object is rolling without slipping. And notice that the mass dropped out as well. Any solid disk has 1/3 of its energy in rotation when rolling without slipping, and any solid cylinder, being the same as a disk, has the same thing. And that's sort of important. Notice we had a lot of extra detail we didn't actually need. Consider a hollow cylinder of the same mass and radius. Which statement is true about the fraction of its total energy that resides in rotational energy? Remember, the rotational inertia of a hollow cylinder is mr squared. So our answer is that k rotation is more than 1/3 in this case. Why is that? Because k rotation, is 1/2 I omega squared again, but I is larger. And so in this case, we would get 1/2, and it's mr squared times v over r quantity squared, or 1/2 mv squared, meaning the rotational energy is equal to the translational energy and therefore is half of the total energy. And a half is bigger than 1/3. All right, a hollow sphere, a solid sphere, and a thin hoop are simultaneously released from rest at the top of an incline. Which will reach the bottom first, assuming all objects are of uniform density? The solid sphere will arrive first, and then the hollow sphere, and then the loop. There's some videos we'll link in the notes that you can look at to prove it. The explanation here is that the larger I is, the larger a fraction of the energy tied up in rotation. They all start with the same gravitational energy, but more of it is in rotation at the bottom for the, say, hoop than compared to the disks or the spheres. And so if more of the energy, if a larger fraction of the energy is in rotation, then obviously correspondingly less of it is in the forward motion of the center of mass. So it is moving on average slower at the bottom of the ramp. Here's a proof of that mathematically, if you want to walk through it. The rotation inertia can always be expressed as, this is bad. Sorry, this went badly. I equals mr squared times some factor k. Sorry, this has gone kind of awry up here, so I'm going to get rid of that and say we have that I is some factor k times mr squared. And the k depends on what you have. I wouldn't memorize this, but it's just good to notice it's always mr squared times some factor, and the factor is larger for the hoop, intermediate for the sphere. Larger for the hoops, least for the solid sphere, intermediate for the hollow sphere. And in each case, we'll do the same analysis. We'll say the energy at the top is equal to the energy at the bottom. The energy at the top, of course, is just mgh. The energy at the bottom is translational and kinetic rotational energies, which is a 1/2 mv squared plus 1/2 I omega squared. But then we can replace I with k mr squared, and replace omega with v over r, and then square it. And so we find we have m in each term, so we can cancel it. Right? We can cancel the m's. And we're left with gh equals this stuff. So the velocity ends up being 2gh over 1 plus k square rooted. Do not memorize this formula. This is not an important formula to memorize, but we can use it to analyze this to show that larger k is, the smaller v is at the bottom, as we said before. And that is really because you're using more of your energy wrapped up inside the rotation, and so there's less available to move the thing forward. All right, a beach ball whose radius is 0.7 meters and a marble whose radius is 0.05 meters are released from rest at the top of the incline at the same moment. Who reaches the bottom of the ramp first? And the answer is the marble, and that's because the marble has a lower I, really a lower factor of k here, but lower I, and so it moves faster at every moment. So it gets there first.